Good afternoon and welcome to the CERIAS Security Seminar from Purdue University. Our speaker today is Steve Dill. He is a chief architect in the cybersecurity solutions area at Lockheed Martin in one of their four major divisions called IS&GS, or Information Systems and Global Services. He's going to be talking today about system engineering. His title is Lifecycle Engineering and Cybersecurity. Steve.
Well, thank you. In the interest of disclosure, I came prepared for a 90-minute talk. So if you have, I was going to interrupt your plans for dinner, but Randy said that I shouldn't do that. So Lockheed Martin is a fairly large organization made up of a number of business areas, and one of them being Information Systems and Global Services. And we in IS&GS view system engineering as one of our core competencies. And so it's kind of a concept that is not well known or well followed among a lot of organizations, especially those who don't deal a lot with the federal government. So I wanted to bring that system engineering perspective to you today. Today we'll provide an overview of how INFOSEC or cybersecurity or information security, or however it's known to you, how engineering requirements and methods fit into an overall systems engineering process. So we're looking at the life cycle of a system. So you can consider information security as a discipline within system engineering, or you can consider system engineering as a discipline that contains elements of system security engineering. But anyway, today we're going to show you some roles of the engineer in the system security lifecycle, in the system engineering lifecycle, and then also some of the processes that are involved. So what is systems engineering? Systems engineering focuses on methods of problem solving and not the solution. So it's the journey that's interesting in system engineering, not the end of the journey. And so we view, if you make the journey complete, or complete's a good word for it, by focusing on the journey, you get to a more effective solution in the end, at the end of the journey. That places an explicit and high priority on things other than the technology. So things like the economics of the solution, the cost, the performance, the safety, a number of other issues that are in totality become the system engineering priority. So we believe that this leads to a more effective solution, and there's a definition of it there from the University of Maryland's School of Engineering, if you want to see the competitor's point of view. So let's consider what is an IT system. It's hardware, software, so on, all these things that show up here. The hardware and software is probably the easy part. The hard part comes in how you handle the data, how people interact with the system, use the system, and get results from the system. The interfaces between your system and somebody else's system. The interfaces between people in the system. We can extend systems engineering to include multiple systems in the goal, so we can have a hierarchy of subsystems as an instance. One of the things we have to consider in this is then the business objectives. So some organizations measure the maturity of systems engineering within target companies. So in in the instance of Lockheed Martin, we are certified at the capability maturity model of 5 for some aspects of our systems engineering, or for almost all aspects of our systems engineering, and our software engineering, and our human engineering, and our resources. So that's a goal for us, is to be at CMMI level 5. Some organizations don't need to, or don't feel they need to get that well mature, or that well defined in system engineering. So you start out with not considering it at all. If you decide then that you need to do it, you can perform it informally. You can plan and track how you improve your systems, or how you operate your systems, how you design them. You can go to well-defined and then quantitatively controlled, continuously improving. Of course, the goal, we believe, should be continuously improving, but not everybody wants to spend that amount of time and effort on their processes. This kind of thing is gone now from the System Engineering Institute at Carnegie Mellon. It's become part of the NSA, and rates their suppliers, their vendors on a scale very similar to this. You started to see this kind of scale in the ISO processes, 27001. So this is kind of the heart of the way we view the system engineering life cycle in Lockheed Martin, and this is a very simplified view of it. So the block diagram in the middle, the wiring diagram in the middle, is a simple representation of a system engineering life cycle. In reality, you go through many of these in any kind of design process, leading to a solution. So you can have this as a waterfall, or you can have it as a spiral development, depending upon what your courses are. But anyway, out of all this, the system engineering life cycle has a number of processes. Some of these are program control processes, some of them engineering, some of them support and organizational. So what might you expect in program control processes? And I'm inviting you to respond. Okay, so cost accounting is one of the program control processes that we might encounter. The program risk management as opposed to the technology risk management. Monitoring of engineering and subcontractor and material suppliers. In the support and organizational processes, we include things like the specialty engineering, human-computer interface engineering, safety engineering, performance engineering. These are all subsets that we view in the engineering pantheon of skills, and we view a lot of these as specialty engineering. And then, of course, the engineering processes. Now we're talking about things like the systems requirements phases, design phase, implementation test phase, and a support phase. And within these phases, we have the period of time when we spend analyzing what the mission of the system is intended to do. And from that, we try to gather high-level requirements. The system requirements can then find themselves as part of a system architecture. And system architecture starts out as a very high-level architecture. It's designed to impart a concept of the system to the viewer of the architecture, to the reader, both to the design people and to the users. So out of that comes things like ConOps, the concept of operations. That breaks down, once you have that level, into you can start devolving your hardware requirements and your software requirements. Once you have the requirements, you can start doing a design. You usually at all the boundaries you see here, there's some kind of a review. You get into then implementation and test, where you actually design the system, you test it, both informally and formally. doing things like code and unit test, which is where you're testing small software modules. You test the hardware, make sure it meets its requirements. And then you transition the system to the real job, to the customer. So you have the deployment of it. You have how the operator operates it, how you're going to support it in the long run, and then in the end, how you get rid of it. And so if you've been thinking about this at all, you realize that all the way through here, there's a lot of roles for a system security engineer or an information security engineer in here. So they have roles to play in the program control processes, roles to play in the development or engineering, and roles in the support. You also have folks who have an interest in this from the customer side who are going to be paying attention to your life cycle. People like the chief information officer, the contracting officer. If you're dealing with a government, the contracting officer's technical representative, who's the person that the systems engineers probably most have contact with. You've got information security program managers on the customer side, the security officers, the acquisition officers, in some cases privacy officers, and so on and so forth. So you deal a lot with those in the program control phase, where you're doing risk management, configuration management, material acquisition, engineering development, and task planning, engineering review boards, quality engineering, continuous process improvement, going back to the maturity model. Covered the I want to cover a little bit more on the supporting processes, because a lot of times we don't consider all the things that go into supporting a program. And some of you, if you're from within the CERIAS, probably are coming from other disciplines, and so this may make some sense. Things like integrated logistics support, user engineering. If you're in the management side of things, you're interested in size, cost, and schedule of the program. If you're a security guy, you're particularly interested in the vulnerability assessments, risk assessments from a technology point of view, but you may also be interested in requirements and verification, traceability, which is another one of the processes that we have to go through. And then we've got things like reuse and database engineering. And let's not forget training. So if I take the information security viewpoint of the systems engineering life cycle, I move boxes around. I can take a somewhat linear viewpoint of it. If we start from the left and work our way to the right, as in the other slide, you'll see some things that fall out at the beginning, some items that go across the whole time frame of a program and its deployment. The